geometry first too. I'm kind of a weirdo. When I was in geometry, I didn't like them though. Geometry is the only math class I ever got B's in. I know B's aren't bad, but I'm a math major, so I got a B in high school geometry. I got a B in college geometry. I got a B in analytic geometry, which is college class also. And other than Calc 3, I got a B plus in because I missed a day because I had the flu and my dumb professor wouldn't let me retake my quiz. Like, make up a quiz. I had a doctor's note and everything. He said, sorry, no makeups. So I don't count that B plus because I shouldn't have had a B plus in that class. But geometry was always my horrible, horrible subject. But then when I became a teacher, I taught geometry. And I loved it. And I was like, man, why didn't I love geometry so much as a student? I didn't. So I feel your pain. One time in geometry class in high school, I got the lowest score out of everyone in my whole class, and normally I did not get the lowest score, and my teacher, like, announced to everyone that I got the lowest score, like, 3 out of 20 on a quiz I got. And even the kid that always did terrible did better than me, and I was ashamed. And it was over little silly stuff, like alternate interior, alternate exterior angles. Isn't that the easiest thing in the whole world? I got a 3 of 20. I don't know what was wrong with me. I struggle. But I'm better now with geometry. Last year you did probability. I think in geometry you do probability, right? I think in this book there's probability. So we're going to kind of go through a lot of stuff today, which is why I printed these out for you. So try to stay with me. Try to stay awake, Bryce, since I printed these out for you. If not, I might throw my pencil at you. But I've saved you a lot of writing. These are some words that I think you should be aware of. Experiment, just in terms of probability, is usually for what we're talking about. If I'm talking about the probability of me tossing a die, then I don't know the results yet, so that's why we call it an experiment. This is kind of the big word I think that shows up on your homework today. Sample space is the list of all possible outcomes. Not just how many are there, but the list. So if I said I have a normal 6-sided die, and I wanted the sample space, what would you say the sample space is for a 6-sided die? Just one die, though, right? That's the probability. The sample space is a list of all possible outcomes. A 1, a 2, a 3, a 4, a 5, and a 6. You see what I'm saying? Like, that's what sample space means. If I'm talking about tossing a coin, the sample space would be heads or tails. Like, it's just a list of what could happen. And I think there's one on your homework today. We're going to do an example in a minute. That it just says list the sample space. So I just want you to be aware that that just means list what could happen. Not what is the probability, but what could happen. Okay? I deleted some of this stuff, so you had to write some stuff down. This is the formula for probability. So probably you're somewhat aware of this, but in case you've forgotten, probability, first of all, this is how we write stuff. If I'm flipping a coin and I want to know the probability of it being heads, we write P and then we put that in the middle. So we say E for the event, the probability of rolling a 5, put the 5 in there, right? So that's just how we write that. And this is the formula. Favorable outcomes, or what I'm looking for over the total outcomes. And so the probability of rolling a 5, there's 1 5, and there's 6 total options. So the probability would be 1/6. I like to remind people that probability has to be between 0 and 1, right? 0 probability would be like no chance of that happening. What's the probability that you will have no homework tonight? 0. What's the probability that I will assign homework tonight? 100% chance. What's the probability that you'll do your homework? Somewhere in the middle. Some people I could say more toward the 0 side. Some people I could say more the 1 side. Some I just don't know. Right? Don't ever give me an answer that's not between 0 and 1. Remember that probability? I like fractions, but this is the one time that I'm okay with decimals and percents. I like percents better than decimals, but a lot of people can visualize a percent chance more than a fraction. So it's up to you how you want to give me those. Okay? So, number 1 here, list the sample space for flipping a coin and rolling a die. We could figure out the total options. That's not the sample space, though. So let's think about that first. How many ways can you flip a coin? 2. How many many ways can you roll a die? 6. Which means there should be 12 total options if you want to know you roll a die and you flip a coin at the same time. How about that for exciting gambling? What would the sample space be? What could I get? I could flip heads and 1. Oh my goodness, how exciting. Heads 2. Heads 3. Heads 4. Heads 5. Heads 6. Or what else could happen? It could be tails and all of that as well. And the nice part about this, one, you don't have to write this out every time unless the problem asks for it. But it's a nice way to check. If you know there should be 12 options, you should be able to list 12 options. Am I going to make you do this if there's like 144 options? No. But you could list some smaller numbers. With me so far? Still awake? We like to do lots of problems about rolling 2 dice at the same time, so I want to make sure we understand that before we move on. It says, what is the probability of rolling 2 dice and getting a sum of 8? So I like to write it like this. Probability of a sum of 8. This is where the fundamental counting principle comes into play if you don't want to have to write them out every time. Let's work with the bottom first, the total options. If I have 2 dice 1, dice 2, how many options are on the first die? And how many options are on the second die? And what do we do when we do the fundamental counting principle? So do you agree that there should be 36 different outcomes when I roll 2 dice? Do you agree with that statement? So now, thinking about that, let's think about all the different ways that we can roll 2 dice and they add up to 8. What do you got? 3 and 5. 6 and 2. 4 and 4. I always say that too. No 7, right? What about 5 and 3? Do I count that too? And 2 and 6. So the question is, do we count it or do we not count it? And if we count that, do I do 4 and 4 twice also? And this is where I go to the sample space. So let's think about if we listed out these 36. And I'm fine if you want to write it down, I'm fine if you don't. I can go really fast if my smartboard will keep up. Do you agree I could roll a 1 to 1, a 1 to 2, a 1 to 3, a 1 to 4, a 1 to 5, a 1 to 6, a 2 to 1, a 2 to 2, a 2 to 3, a 2 to 4, a 2 to 5, 2 to 6, 3 to 1, 3 to 2, 3 to 3, 3 to 4, 3 to 5, 3 to 6, 4 to 1, 4 to 2, 4 to 3, 4 to 4, 4 to 5, 4 to 6, 5 to 1, 5 to 2, 5 to 3, 5 to 4, 5 to 5, 5 to 6, 6 and 1, 6 and 2, 6 and 3, 6 and 4, 6 and 5, 6 and 6. Does that give me 36 outcomes? Are these in there twice? Like, is that in there? I have a 3 and a 5, and a 5 and a 3. I always say it has to do with 2 different dice. So you could roll a 3 on one and a 5 on another, and a 5 on one and 3 on the other. That's 2 different ones. So then people say, well, what about the 4 and a 4? Why isn't it in there twice? And my best explanation is to look at this. 4 and 4 only shows up one time. And the reason that I say it doesn't work is unless you mark the dice, do you agree that you wouldn't know that, like, I don't know. A 4 and a 4 is a 4 and a 4 even if they're switched? No? Yeah. What? They all add up to 8, right? Then you had to write them all out to see that, but yes. So, I just like to point this out because people always really struggle with it on whether or not, some people disagree that you shouldn't include these. Some people want to include 4 and 4 twice. And I just like to show you that this is all of the sample space. And you can see that each double only shows up one time because it's the same number. So it's no different if you switch the dice. But it is different 3 and 5 and 5 and 3. I don't know if that's believable or not, but anyway, I think there should be 5. 5 out of 36. And the reason that I say percents or decimals are okay is because a lot of people struggle. 5 out of 36, like visualizing that. But if you divide it out, 5 divided by 36, that's like 13.9%. And a lot of people can visualize that a lot better. I'm okay with giving me an answer of 5 over 36. I like fraction answers. Some people like decimals or percents. Okay? There's definitely questions on your homework about 2 dice at the same time and whether you roll an even number, or whether you roll an even sum or an odd sum. So maybe having that written out isn't the worst thing in the whole world. Okay, there's a lot of stuff here, and I just want to kind of cover it up, even though it's all printed out for you, just so you can kind of see. You learned a lot of rules about probability in Algebra 2, and we're kind of summarizing them all today. Independent events are events that don't affect each other, like our first thing, flipping a coin and rolling a die. It doesn't matter what I flip on the coin, the die is completely separate from that. Those are independent events. And here's the big idea. When you see the word and, if I flip a coin and roll a die and I want to know the probability, you're going to always just multiply those 2 probabilities together. So and means multiply. It kind of goes right with our fundamental counting principle. You take the number of options and you multiply them together. Another way to think about independent events would be if you replace it when you do it. So think about those problems like if you have a bag of marbles and there's so many yellow and there's so many green. If I draw out a red and then I put it back in and I want to draw out another red, it's a new event. It's completely independent because I put it back. As opposed to if I'm talking about a dependent event. Dependent event would be like without replacing it. It's still and. What's the chance of drawing a red marble and drawing another red marble if I don't put the first one back? But the difference is the second event is dependent on what happened on the first event. Because if I keep it out, then I've changed the probability. And so it's still multiplication, you just have to think about what happened. And so I think I have a couple little examples here that you're going to remember doing problems like this last year. And this is where in second hour when I had to write this, we decided I probably should have printed our notes out. But you know, it was Monday after a long break, I kind of didn't think things through. But it says, find the probability of drawing a 7 from a deck of cards, putting it back, and then drawing another 7. I'm always interested to find out how many people don't know much about cards when we get to problems like this, because I know how many cards are in a deck, because when I was a child, my stepdad was really mean and said, hey, you want to play a 52 card pickup? And I said, yeah, and then he threw all the cards on the floor and told me to pick them up. Fun game. So I always knew there was 52 cards in the deck, but some people didn't know. So there's 52 cards in the deck. If you don't know those things, you might want to write that down. There are 4 suits, so 52 divided by 4, there are 13 of each card. I mean of each suit, right? 13 hearts, 13 diamonds, that's what I mean, not 13 of each card. But some people don't know this, so I like to tell you. I don't want you to be at a disadvantage because you don't know about this. How many 7s are in a deck? 4, because there's 4 suits. So what's the probability of drawing a 7 and drawing another 7 if I put it back in? So we said there are 4 7s, and how many cards again? 52. That's the probability of drawing 1 7. And then I'm going to look at my 7, and then I'm going to put it back in the deck and reshuffle, which means what's the chance of drawing another 7? Still 4 out of 52, because this is an independent event. Yes? And that is, if I reduce that, 1 over 169 chance of that happening. Again, I'm fine with that answer. If you'd rather change it, I like percents, but you could do decimals too. But if I change it to a percent, that's like 0.59%. So not even 1% chance of that happening. Do you ever watch those poker tournaments where the announcers is like, there's a 4 in 57 chance of that happening right now? And I'm like, do they have all those listed out? Do they just know all those chances? I don't know. That's amazing to me. I've been using PDFs all day, can you tell? I just tried to move the whole board up. So look at this one. Same question, except find the probability of drawing a 7, keeping it, and then drawing another 7. This has now become a dependent event. That's totally not spelled right. Dependent. Still drawing 1 7 and still drawing another 7, but you have to remember that the second 7, there's one less card now, right? So the first 7, still 4 out of 52 chance. So I drew a 7 already. I have it in my hand. How many 7s are left? And how many total cards are left? One out of 221 chance of that happening. Or that would be like 0.45% chance. And it should make sense that that's a less chance because there's one less 7 left in the deck now. Maybe. Vague memories of this from last year? Yeah. Is that right? Small chance. Something that I don't know that you did last year was talk about the complement of an event. And a complement of an event, another way to think about maybe is like the opposite. And the definition is the collection of all the outcomes in the sample space that are not in A. So if I said, what's the probability of flipping ahead? The complement of that would be what else could happen besides flipping ahead? What's the other outcome? Tails. So there's only 2 options, so that one's easy. The probability of rolling a 5 would be there's 1 5. How many not 5s are there? 5 of them, right? And so a complement is like every way that it can't happen. And the way we write complement is with this little, I call it a prime. It's not a 1. I think of it more of like an apostrophe. In calculus, we use that prime to show derivatives. It's just a little math symbol. But A prime means the complement, or how many ways can't it happen. And so I wrote here that when you add up all the ways that something can happen, plus all the ways, the probability that it can't happen, it should add up to 1. Does that make sense to you? If I say how many ways can I roll a 5, plus how many ways can I not roll a 5, does that add up to 1 altogether? 1 out of 6 plus 5 out of 6. I think that's always going to work. How many ways could I draw a 7 out of a deck of cards to how many ways could I not draw a 7? It should always add up to 1. So we're going to look at a problem tomorrow, one that's later in the homework that usually people have trouble with. And I'm going to show you, hey, if you just do the complement of the event and then take 1 minus that, it's a lot easier than actually doing the actual problem. And people are always like, oh, and that's kind of where complements are useful. Sometimes it's easier to find the complement and then subtract from 1 to get the right answer. Okay? So we'll talk about that more tomorrow, I'm sure. One more thing before we can get to some probability. The big thing that I want you to know, besides the other probability, is the difference between when to multiply probabilities and when to add probabilities. Multiply is if you're doing this and this. I want to know the chance of drawing a 7 and drawing an 8. The chance of flipping a coin and rolling something on a die. As opposed to this or that. I want to know the chance of rolling a 7, not rolling a 7, drawing a 7 or an 8 out of a deck of cards. So if you see the word or, you need to make sure that you know that means add. I threw in some extra math language here just because it is precalculus, and I like to show you this stuff sometimes. We've talked about this symbol a lot. This means union, and union, another word for union is or. So when this says the probability of A union B, you can change that to or if you prefer. I just like to show it to you. So the probability of A or B, the big idea is we're going to add. We're going to take the probability of A plus the probability of B. Then you have to subtract out. This means intersection. Or another way to think about that is the word and. And the best way I can explain this is with Venn diagrams. So let me just draw two little circles up here. If this circle represented the number of ways that A could happen, and this circle represented the number of ways that B can happen, do you agree that sometimes they could both happen at the same time? So just subtract that out. And so maybe if it helps you, you could write here, when A and B both happen. And the best way, my examples, I always like to use cards. If I said, what's the chance of me drawing an ace or a red card? Could I draw one card that meets both of those requirements? I could draw an ace that's red. And so you have to subtract out when they happen at the same time. Otherwise, you're counting some things twice. If you count all the aces and you count all the red cards, you've counted some twice. So you have to subtract it out. So that's where this formula comes from, is that if it can happen at the same time, you got to subtract it out. Sometimes you don't have to subtract it out, and I always say, just remember this formula, and sometimes you subtract out nothing. But your book does show you that if they're mutually exclusive, which was a vocab word from last year, that means they can't happen at the same time, then you don't have to subtract anything out, because there's no overlap here. But I say if you just remember this formula, you don't need that formula, right? Because you would just subtract out nothing. Yes, no? Anybody have any clue what I'm saying? That's why I don't like to write your notes out. I feel like I lose you even faster. Bryce is already sleeping. So let's look at these two examples here. Standard deck of cards. I want the probability of drawing two cards and getting a 7 or an 8, and then just getting, a 7 or a heart, or a 7 or an 8. A 7 or a heart. Could that happen at the same time? Yes, so that means you have to think about, to find this, a 7 or a heart. I put hearts here because it's my best one I can draw. Diamonds. I can't draw the other ones. Spade. Club. I can't do those. We're going to take the probability of a 7, or means add the probability of getting a heart, and we're going to subtract out the probability of both a 7 and a heart. Seven's my favorite number. We're using it again. How many 7s in a deck of cards? 4. How many cards in a deck again? 52. How many hearts are in a deck of cards? 13. If you didn't know, you could just count 2 through 10, Jack, Queen, King, Ace. But there's 13. Or 52 divided by 4. Minus, how many cards are both 7 and a heart? The 7 of hearts. And here's the best part about these fractions. They're all common denominators. We don't even need calculators. Right? Is that 4 out of 13? Which is about 31%. I'm going to say about 30.8% chance of that happening. What about drawing a 7 or an 8? Could that happen at the same time? No, it's okay if you still think about the same formula. You just don't have to subtract anything. You really only have to do the probability of getting a 7 plus the probability of getting an 8. If you weren't sure and you said subtract out the probability of getting a 7 or an 8, or 7 and an 8, you would just subtract 0. So that's why I said you don't really have to think about it as two formulas, because you just subtract nothing sometimes. Do you agree that this is 4 out of 52 and this is still 4 out of 52? When you're doing OR, it's like both separate and you just add them together. Just 8 out of 52. Which is about 15.4% chance of that happening. Which it should make sense. The chance of drawing a 7 or a heart is better than drawing a 7 or an 8 because there's more hearts. Okay, ready for the good stuff? Not all probability is as simple as this, right? Sometimes it's a lot more complicated. And maybe we have to use some combinations and get exciting with our probability. Like this. This is a good little spelling word for you. See what that word is? Euchre. Did you know that's how you spell euchre? There you go. Euchre, a lot of people know euchre, but some people have never played it before. Euchre is just a card game, but you don't use the whole deck. You only use 24 cards. You only use the 9, 10, Jack, Queen, King, Ace of each suit. And so 9 is the lowest card that you have. And it's kind of a weird game if you've never played. It takes a while to learn trump, and sometimes a spade is a club, and a club is a spade, and it's kind of a weird game, but it's a fun game. And when you're playing euchre, each person gets 5 cards. So I said, let's find the probability of getting a hand of all spades. So think about if we tried to work all this out, because if we were trying to get a hand of all spades, on the top, we want to get how many all spades could we get, right? So I'm just going to write this out for a minute. We want how many are all spades. And then the bottom would be how many different hands could you get, 24 cards, if each person got 5. So we want how many total hands are possible. Some people always struggle with probability, and they say, how do you know when to use combinations and when that you can just count them up? And I don't really have a good answer for that, except for if you tried to list out all the different ways that you could take 24 cards and pass them out 5 at a time, do you agree that's going to be a big list? So for me, in my head, I always think, there's no way I can list those out. I better be using a combination because there's going to be a lot of ways that I can put those cards out. So let's do the bottom first. I do better with that. How many total cards are there? 24 cards. And how many do you give everyone? 5. So the total number of hands that you could give someone would be 24 choose 5. Which is a really, really big number. Um, 42,504 ways that you could get a hand of cards in euchre. Think about if you played with all 52 cards, how many different hands you get. Like for poker and such. A lot. That'd be 52 choose 5, or how many cards you're doing. What about spades? How many spades are in this deck that we play with? 6, because there's 9, 10, Jack, Queen, King, Ace. So there's 6. And how many do you get in the hand? 5. So that could be 6 choose 5. Which I think it just happens to be 6. And that would be 6 over 42504. Which is really, really, really small. 0.014%. I've played euchre a lot, and I've never got a hand of all spades. So, you know, it should make sense that that's pretty small. So I just want you to think about this today. I'm not actually going to do this one next because I want to just leave you this to think about because I think there's one like this on your homework tonight, and I want to leave you to think about it, and then we will talk about it tomorrow. But the same idea is you can set up different problems. I normally do this little Yahtzee lab after this lesson, but we're so short on time that it's not going to happen. But where we figure out like what's the chance of rolling a full house and a small straight and a large straight, and what's the chance of rolling a Yahtzee when you play Yahtzee, and it's a really, really small chance. But we don't get time to do that. So we're just going to look at the one on our homework tomorrow and kind of go from there. So I'm going to actually leave this one. But just know that some of the ones on your homework tonight, especially towards the end, use combinations, and we'll kind of pick up with this tomorrow. All right? And here are my overall hints about probability, because people get really confused on it. Figure out if you're adding or multiplying. If you're adding, you should be able to say the word and. I'm doing this and this. A red marble and an orange marble. I totally did that wrong, kids. That's this. And is if you're multiplying. And if you're adding, you should say or. I'm drawing a 7 or an 8. A spade or a club. Right? So think about those words. I always say that in my head. Sometimes you will need combinations, not a lot, but you will need those on your homework tonight. And then remember, like, to make sure your answer makes sense. It should be between 0 and 1, and not anything different than that. And I'm okay with decimals if you give me decimals. So on your homework today, this is homework 9-3. It's only one day of it. I kind of just picked a bunch here. I'll tell you some of the ones at the beginning people always get really confused on. So if you get a chance, we have like 5 minutes, you can look at it. They give you a table that already has the probabilities, and people always get so confused because they think they need to figure it themselves. But they're just decimals already, and they just ask you to do like a red and an orange, and you just multiply them, or you a red or an orange, and you just add them. So it's not supposed to be hard, but people always get confused by it. So get a chance, get your book open, get your paper labeled, and look at those first few, and see if you have questions on them. And then we'll go on to 9-4 tomorrow.
Practice Wednesday morning and Friday morning. Do you have it every morning?
Sorry.
Not Tuesday. But you have it the rest of the week. So you love Tuesday.
Don't forget that test corrections are due on Friday of this week, and if you want to retake one or both parts of that test, this week is it. And you have to turn your other test in when you retake it, because I have to know what your other score was if you're only retaking one part, especially. But that's it, this Friday. Don't forget that. I kind of had a long break. before Adrian come in. What do you do with negative x numbers? Yes. So then you have to move 2 bucks. But yes, that's the right idea. So if your plate starts, then you have to move that negative 4 to the front. That makes negative 4. So write out what you have and then let's look at it. You can write it right here. But you should not be writing log more than one time. They make a pair. So like, if you only say I only have log one time, you only have log one time. It should be one log out here, and then do that. When you're putting it back together, you only write it one time. Think about this. You only write it one time. No, it's not negative. You only do it one time. That's rolling 2 dice. It's just like what we did about the sum of 2 dice. So sum of 1 is greater than that. So look on, if you write that list out that I wrote, like 1, 2, 3, 1, list. So you need to think of all the times that one dice, like pick one to be right. It doesn't matter which one. But you have to pick all the times that one is bigger than the other. So like, if you pick the first one to be red, one never would be bigger. Like if you do all the ones first, right? But like 2, 1, 3, right? That's the only one of the 2. What about 3?
Hey, Boston Double, please. I need Joe French, Vicky DeCraddick, Kelly Chavon, Victoria Honey, Nathan Sheets, Lucas Callahan, Emily Bob, Megan Arnold, Dallas, please.
4, 1, 4, 2, 4, 3, 5, 1. So then on 6s, all those are going to be. So it's going to be a lot of them. But it doesn't matter which one's red and which one's green, as long as you just pick one to be red. Like the first one's red or the second one's red. You know what I'm saying?
I can see like red, green, and then however many goes the first
Yeah, then they go to your
this number
over the total. The total is 36, right? So you just need to add up how many of these ways you have. You see what I'm saying about that? Like, how many is it? No. You're just gonna add. How many times is the red die greater than the green die? So you're just adding them up. Like, as these are all the same. Now just go through 5, 1, 5, 2, 5, 3, 5, 4, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and just add them up to 36. Does that make sense? And it kind of throws people because they're colored dice, but it doesn't matter. Just pick one of them. Does that make sense?
Yeah.
Okay.
For transcriptions, would you